All right, we are going to do a quick review of things that we talked about last year. And when I say quick, I mean quick. If you really need to look at things again, I posted the first 4 videos we looked at for energy last year already on the website. I'll post the rest of them probably sometime tomorrow. So the first thing that we're going to talk about is the concept of work. So with work, what we did was say that work last year was equal to a force times a displacement or distance. And really we talked about the parallel component of work. So it was force times your displacement or your distance times the cosine of the angle in between the two. But we're in AP Physics now, and we're going to get to deal with integrals on this. So the way that we're going to define work now is the integral of force with respect to displacement. And that little dot there is a special kind of dot. That dot right there is a special kind of dot. It's for the dot product. Now, the dot product is a special mathematical term that we're going to use really. So when you multiply 2 vectors, to get a scalar. So basically I'm putting 2 vectors together and I'm getting just a number out of it. So this tells us that work is a scalar. It doesn't have any direction to it. It can be positive and negative. The other thing about the dot product is that only parallel vectors or parallel components matter. And this is something that we looked at last year with work. If we have a box, there's my box, mass M, and I apply a force this way, I know I've got weight, I know I've got the normal force. Let's pretend that there's some friction backwards. When we look at this, we can't use all of F, so we're going to have F cosine theta this way, F sine theta this way, and if our displacement is in this direction, each one of these forces is going to do work. So we'll go ahead and talk about net work with this as well, and what the dot product means. The dot product means that we're just going to be taking this component of force and this component of our displacement and multiplying those 2 things together to figure out how much work that force does. So the work done by F is just going to be F cosine theta times delta x. The work done by the weight is going to be 0. Weight is pointing down, so it's not going to do anything to help my object move forward. This is a little bit different than how we think of work. Same thing with the work done by the normal force. That's also going to be 0. The normal force points up, we move over, so the normal force isn't contributing to that work at all. And then we have the work done by friction. That's going to be friction times our delta x, but guess what? That friction is going to be negative because friction is in the opposite direction. Friction is in the opposite direction from my delta x. Those 2 things have a conflict with each other. So friction is going to be negative. You can have negative work. We'll talk about what positive and negative work mean in just a second. But negative work, sorry about that. Whoop. Negative work is possible. In order to get the net work, we would just add all of these things up. So when we do that, F cosine theta times delta x plus 0 plus negative friction times r delta x gives us our net work. That is the overall work that we do. And this leads us into our next thing, talking about what net work is. This is the Work-Energy Theorem. So here we've got net work, the sum of all of the work done by all of the forces acting on my object. Net work is equal to the change in kinetic energy of an object. Well, KE is what we used for kinetic energy last year. We're grown-ups now, so we're just going to use delta K. So what we have for that is 1/2 mv final squared minus 1/2 mv initial squared. And that defines kinetic energy for us as 1/2 mv squared. But what this lets us do is talk about what positive and negative work really are, and really talk about what work is. So, looking at that, work is the quantity that changes the kinetic energy of an object. So positive work increases kinetic energy, and negative work decreases kinetic energy. So when we're looking at that, F cosine theta times delta x, we are pushing this object forward. It makes sense that that part of my work is going to act to speed it up. And then when we look here at what friction is doing, friction as a force acts to slow objects down. It resists motion. So that's going to slow us down. Now the net work, is closely related to the acceleration of an object, and I'll let you watch that video from last year to get the basic idea of what happens. But here, net work is equal to the sum of the forces acting on an object times its displacement. That's a good way to look at net work. You take the sum of the forces, multiply it by the displacement, and it's going to give you an expression for net work, which will in turn give you an expression for the change in kinetic energy of the object. I want to go ahead and stay on this page for this. The concept of power fits in with what we talked about last year. So power is the rate at which work is done. So last year, power was work over time or the change in kinetic energy over time, or force times distance over time, which was force times velocity. This year, power is going to be the derivative of work with respect to time, or the derivative of kinetic energy, if we have a function for kinetic energy with respect to time. These are just different ways that we could use work, power, and energy. I think what we did today in class were some good examples of how to look at all of this. So we're going to go ahead and move on to talking about conservative and non-conservative forces.